Good afternoon and welcome to Uni4Me Live, and I'm Martin Webster. In case you haven't joined us before, Uni4Me is a website with over 58 higher education organisations all contributing to it, adding online activities which you can access for free. And I'm delighted to say that we've been joined this afternoon by Scott Marley. Scott does a lot of physics outreach work for Imperial College London, and he's going to talk us through some exciting stuff. I have to mute my YouTube now. And I'm Martin. There we go. Sorry, Scott, technical difficulties,
Sorry, no,
but I shall hand over to you now.
Thank you very much. Okay, hello everybody. So my name's Scott. Thanks for the introduction, Martin. And I do work for Imperial College quite a lot, doing various bits and pieces. Today, I thought we'd do something a little bit different, maybe, to some of the videos that have been on here before. And that's we're going to sort of take a bit of a deeper dive into a topic that I think's really interesting. And that's something called gravitational waves. Now, if you bear with me a moment, I'm just going to switch over here to my presentation, and then we'll get started. Okay. So gravitational waves, very interesting, very weird. They're actually predicted a very long time ago by a chap that some of you guys might have heard of called Albert Einstein. And he came up with this idea that maybe if we've got objects moving around and they're moving through space, then they might leave behind ripples. And that's a kind of a weird concept to get your head around. So we'll go into that in a bit more detail. Let's start, though, even longer ago than that. Let's start even before Einstein, and let's start with optical astronomy. So here's a picture of the moon, and for most of human history, we've only been able to see the night sky using visible light, so using our eyes. And then in the early 1600s, we moved on to Galileo, and Galileo was famous for inventing the telescope. Didn't actually invent it, but he was one of the first people to use it scientifically to look up at the night sky. We then have to jump forward quite a long way, another few hundred years. And in the 1960s, we started doing radio astronomy. Now, radio astronomy is using radio waves to look up into space instead of the visible light that we normally use. This is the Arecibo Radio Telescope in Puerto Rico, and it was on the news fairly recently because it fell apart. One of the cables snapped, holding up that detector, which you can see at the top up there, and it actually crashed into the base of the telescope, and it's destroyed it, unfortunately. It was the biggest radio telescope in the world until that point. There is now a bigger one, actually. It's in China, and that radio telescope is 500 meters across, so absolutely enormous. Now, what kind of pictures of the night sky can we see if we use something like a radio telescope? Well, if you look up into space with a normal telescope, you might see something like this. And that fuzzy blob you can see in the center just there is a galaxy. It's called Hercules A. It's actually an enormous galaxy. It's about 1,000 times more massive than the Milky Way. And it's got a central black hole of about 4 billion solar masses. So that means 4 billion times heavier than the sun. But it doesn't look like much if you look at it with visible light. If we use our radio telescope, though, we can actually see these enormous jets, these big pink emissions coming out of this galaxy. And what you can see there is the result of the black hole chewing stuff up, shredding it and throwing it out in these giant jets that are thousands of light years across into space. Moving on a little bit further, we upgraded our telescopes and we started putting them up into space. This is one of the most famous ones. It's the Hubble Space Telescope. It's getting pretty old now. It's been up there for 27, 28 years. Pretty long time for a satellite. And Hubble can see in both visible light and in infrared. If you look at our nearest galaxy, the Andromeda galaxy, in visible, so you can see at the top, and in infrared, you can see just behind me here. And if you look at those pictures carefully, you can see that the darker areas on the visible image are actually some of the brighter areas on the infrared image. You can see my mouse pointer on here at all, but these dark areas just here correspond to these bright areas just here. And the reason they look like that is because those dark areas, they're not lack of stars, they're actually dust that's blocking out our view. Now, dust happens to be transparent in the infrared. You can see through it. So by using an infrared telescope, we can actually see the light coming through from the stars behind those dust clouds. We can also look at the sky in X-rays, and this is the Chandra X-ray Observatory, and this was launched in 1999. It's very difficult to see to build an X-ray telescope, because one thing hopefully you guys know about X-rays is they tend to go through stuff. That makes it difficult to make X-ray mirrors. But again, if we look at a patch of the night sky with our eyes, we might see something like this. If we turn on the Chandra X-ray telescope, it might look something more like this. And this is the Tycho supernova. And the Tycho supernova is a star that exploded about 1572, I think it was. And the two different colors here, basically they're showing you that the remains of that enormous explosion. The red parts are the expanding debris cloud, and the blue parts are like a shock wave coming off from that explosion. So 500 years later, and we can still see that explosion up in space. We can also look at the sky in gamma rays as well. This is the Fermi Gamma Ray Observatory, which was launched in 2008. And this is used to look at very odd things called fast gamma ray bursts, very strange objects in the night sky. Now, all of the things we've just mentioned are all part of the electromagnetic spectrum. And that goes all the way from radio waves all the way up to gamma rays, and we increase in energy as we go through that spectrum. The reason why gravitational waves are so exciting is because they're nothing to do with the electromagnetic spectrum. So that means if we can find them, if we can sort of use a telescope to detect these things, we've actually got a completely new way of observing the universe. So what are gravitational waves? Let's talk about what they are and how they're made. In order to do this, we have to understand a little bit about Einstein's theory of general relativity. Now, don't worry, we're not going to go through the mathematics of this. It's a little bit complicated. But very basically, when you have an object, a massive object like the sun in this image, for example, it actually curves space itself. Now, there's a chap called Archibald Wheeler who came up with a good description of this. And he said, basically, general relativity, matter tells space how to curve, and space tells matter how to move. So imagine I take a planet into this picture you can see behind me, and I roll it across that green grid there, because that green grid is representing space being curved. You can hopefully imagine that planet might fall down into that dip and start to orbit, start to spin around. And that's how we think gravity really works. Now, Einstein published his ideas on this in 1916. And as I said at the start, he also thought that as objects move through space, maybe it would cause ripples. So here we can see two objects in space moving around each other. So just like if you move your hand through the water in a pond, you're going to leave some ripples behind your hand. The same thing happens in space. As these objects are moving through space, it's causing ripples. Now, those ripples are gravitational waves. Now, this simulation we can see here are two massive objects. They're called neutron stars. And neutron stars are what's left behind when giant stars explode. And we've just got their cores left. They're quite small. They're only about 10 kilometers across, but their mass is about twice that of the sun. So 10 kilometers across, but 2 times the mass of our sun. So incredibly dense, very, very high density. The main fact that's normally taught about neutron stars, it varies quite a bit, but a sort of matchbox size, a small piece of neutron star, maybe a few centimeters on each side, would weigh about 5 trillion tons, which is about the same as Mount Everest, something along those lines. Neutron stars are really weird. The gravity is actually so strong on the surface of a neutron star that you can see more than half of the surface at once. So the gravity warps the light from behind the star round to the front, so you can actually see more than half the surface. Very, very weird things. Now, these gravitational waves will then flow out through space, and they're kind of hard to imagine. They're actually like 3-dimensional waves. So normally when we draw a wave in physics, we draw it as a flat 2D plane. Don't we draw a sort of sine wave or a cosine wave? But for gravitational waves, you've got to imagine them being in 3 dimensions. So something a little bit more like this instead. So let's imagine there's a gravitational wave right now running across you left to right like this. It would be making you go slightly taller and slightly shorter. It'll actually be warping you and stretching you if a gravitational wave passes through you right now. Now, the thing is, you probably wouldn't notice it. Firstly, because that effect is very, very small. And secondly, because everything else is also getting slightly taller and slightly shorter. So it kind of looks normal to us. Now, on the previous simulation, we talked about neutron stars being very small and very, very dense. And one thing that's even smaller and even denser than a neutron star is a black hole. Now, black holes curve space dramatically, and that's because they're incredibly dense. And the denser an object is, the more intense the gravitational waves are that are being given off by this object. So in order to detect these things, in order to find gravitational waves, what we're going to look for are two incredibly dense objects like black holes orbiting around each other and colliding, merging together. Now, this is a simulation of what that might look like. So we have the two black holes orbiting around. You can see the green waves, so the gravitational waves radiating off into space. And as the gravitational waves radiate off, they carry away energy. Because the energy is being carried away, these black holes are going to get closer and closer together. And eventually, they're going to merge. And as they merge, we get this massive burst of energy, this enormous burst of gravitational waves. And that's what we're going to try and detect using our gravitational wave detectors. So here's a more accurate simulation of what that might actually look like. And about 1 billion years ago, a few hundred miles apart, these two black holes were orbiting around each other at almost the speed of light. As they orbited around, they lost energy. Imagine whirling something around your head like this, right? As you slow down, as you lose energy, the object you're spinning falls in, doesn't it? It gets closer and closer to you. As they merged together, they actually released about 100 times more energy than all the stars in the universe combined in that instant. And they produced a new black hole about 62 times the mass of the sun. So for 1 billion years, those gravitational waves traveled through space. And eventually, a long time later, they managed to reach the Earth. Now you can see on the animation here, it says scale of effect vastly exaggerated. So as these gravitational waves pass through the Earth, they're going to cause the Earth to wobble and to change shape. It won't quite look like this. The effect is very, very small. And these gravitational waves from 1 billion years ago passed across the Earth on the 14th of September, 2015. Now, conveniently, about 2 weeks earlier, we just switched on the first gravitational wave observatory, or the first one that was good enough to detect this kind of event. This observatory is called LIGO, and it stands for Laser Interferometer Gravitational Wave Observatory. And it's basically two concrete tubes, concrete pipes. You can see those in the picture behind me, 3.5 meters in diameter, about 4 kilometers long, and you can see they stretch off into the distance. There's actually two of these detectors. One is in Louisiana, and one is in Washington State. You can see these two things just here. Now, these pipes are so long that they have to be 1 meter higher at one end than they are at the other end to account for the actual curvature of the Earth. And inside these tubes, it's a near perfect vacuum, which is about 1 trillionth of normal air pressure. Incredibly, these tubes are only about 3 millimeters thick, so it's quite impressive that we can manage to do that. So what are they, and how do these things work? Well, they're a physics device called an interferometer. Let's have a little look about how an interferometer works. Hopefully, if you're in year 12 or in year 13 and you're watching this, you'll have covered waves before, and you will have talked about interference and superposition. So that's how this thing works. Let's have a look at an animation here. What we have is a laser, and that laser fires a laser beam, hits a beam splitter. You can see that in the middle just there. And half the laser light goes off to one mirror, and half the laser light goes off to another mirror. So we can see hitting the beam splitter, laser light splits, goes down those two arms. Remember, they're 3.5 kilometers long, or about 4 kilometers long, goes along those arms, bounces off a mirror at the other end, and then they come back towards the beam splitter where they recombine. And they recombine and reflect onto a detector. You can see just behind my head here. Now, the thing is, if the arms of these detectors are exactly the same length, then that light will come back in phase. If light is in phase, it means the waves are adding up, right? It's what we call superposition. And as the waves add up, that means we're going to get a bright spot being formed on the detector. If one of those arms is slightly longer or slightly shorter than the other arm, they might come back in antiphase. And if the waves are in antiphase, that means a peak and a trough will meet and cancel out, and then we'll get no light at the detector. So as this gravitational wave passes across the Earth, it's going to stretch one arm a little bit more than it stretches the other arm. And therefore, the amount of light we see on the detector is going to vary a little bit. It's going to get brighter and darker and brighter and darker. And that's how we can detect these gravitational waves. Now, in theory, that doesn't sound too complicated. Well, maybe it does. But if you're a physicist, it doesn't sound too complicated until you start thinking about the practicalities of actually doing this. So let's talk a little bit about the engineering of this and how on earth this works. So here you can see an absolutely not posed photograph of a chap inspecting one of the mirrors at the end of one of these laser arms. Each mirror is about 40 kilograms in weight, and it's made of silica, basically sand. It's polished to be incredibly smooth, to nanometer smoothness. And it has to be so precise that when the laser beam from one end hits the mirror, even though those mirrors are very, very shiny, it's still going to heat that mirror up a tiny little bit. And so there are actually other lasers on the other side of the mirror to heat up the exact opposite part in the same way to cancel that out. So that's how accurate it has to be. Here's an image of the whole mirror device that's supported from the roof of the tunnel. And the thing is, we need to isolate this incredibly well. The thing is, this entire setup is just looking for small vibrations. And so it will detect everything. Nearby roads, it'll detect weather patterns on the other side of the continent. It could even detect staff riding their bikes along the side of the experiment. It can detect every earthquake on Earth. And so this has to have active dampers. And what that does, it cancels out any of this extra external noise. A lot of you guys might have noise cancelling headphones. If you have Apple AirPods or something along those lines, they have a noise cancelling function built in. And the way that works is the AirPods listen to the sound on the outside, and then they play back into your ears the exact opposite sound, right? The inverted sound, and that cancels out. We have to do the same thing here as well. In order to isolate this from the roof of the tunnel, this entire arrangement, 360 kilograms, absolutely massive, is suspended on 4 glass threads that are only 0.4 millimeters thick. So this entire 360 kilogram thing is hanging from the ceiling by 4 glass threads only 0.5 millimeter thick. We do that to thermally isolate it, in other words, cut it off from the thermal noise in the tube. The distances between this mirror and the laser has to be maintained to about a picometer, or about 1/100 millionth of a human hair. So hopefully already you can see that the engineering that goes into this is just extraordinary, incredibly exciting stuff. Here's a picture of the laser hall where the laser is generated. Even this is not simple. So the laser begins its life as a 2-watt laser. Now, if any of you guys play with lasers at home, if you're doing that, make sure you're wearing the appropriate eye protection. You only get one set of eyes, right? And you can go blind pretty quickly. A 2-watt laser is very, very dangerous. And it can easily burn through stuff. And you might have seen videos on YouTube of people setting fire to stuff or popping balloons or whatever. But 2 watts is nowhere near enough for this. And so that 2-watt laser in this big system here is actually amplified up to 750 kilowatts. Now, if you think a normal kettle is about 2 to 3 kilowatts, it's an enormous amount of laser power that's required. So you definitely don't want to be sticking your head in this thing. So the engineering that goes into this is just utterly phenomenal. And what does this get us? What do we get out of this? Well, let's imagine for a minute that we're looking here at a hydrogen atom. So this is the electron flying around the outside. And let's zoom right in to the nucleus. And we might know that the nucleus of a hydrogen atom is just a single proton. And all of this incredible engineering means that we can detect changes in the length of those tubes down to 1/10,000th of the diameter of a proton. So these numbers are just very, very difficult to wrap your head around. So what do we find? Well, we talked about that gravitational wave that traveled for 1 billion years through space. And in September of 2015, this is what we actually saw. Think about those objects orbiting around each other, and they're getting closer and closer and faster. And that's what we see on these 2 graphs you can see behind me just here. You can see that the amplitude is increasing, and you can also see that the frequency is increasing as well, so the wavelength is decreasing. It's exactly what we'd expect to see. These 2 black holes orbiting around closer and closer and closer. Right at the end, we get this big burst of energy, and then it goes quiet because they've merged into a single black hole. And this is where having 2 detectors comes in really, really handy, because we can correlate that data. We can check that what we're looking at is actually a gravitational wave and not like a local vibration that was picked up by one detector or the other. Now, these 2 detectors are spaced about 3,000 kilometers apart, one in, say, Louisiana, one in Washington. And we could say, well, maybe it's an earthquake. Maybe we haven't detected gravitational waves. Maybe we detected an earthquake. The thing is, we know how fast earthquake waves travel. And they travel at the speed of sound in rock, which is usually a few kilometers a second, something along those lines. Now, Einstein predicted that gravitational waves would actually travel at the speed of light. And so what we did is, when it was detected in Louisiana and when it was detected in Washington, the time difference between those 2 worked out to be that it would the wave had to travel at the speed of light to get between those two places. So that's one of the reasons that we were pretty sure this was a gravitational wave. Now, another good reason for having two detectors is it means you can start sort of working out whereabouts these waves are coming from in space. Now, with only two detectors, you can only make a rough approximation about where these waves came from. You actually need at least three detectors in order to get an accurate position. It's a little bit like GPS. So if you think about how GPS works, we have all the GPS satellites orbiting around us up in space. And your phone needs to be able to see at least three of those. And then we can do something called trilateration. It's like triangulation, but in 3D. So we need at least 3 points in order to work out where you are for GPS, or where the source of gravitational waves is up in space. Now, as it turns out, that's fine, because fairly recently we've had a few other gravitational wave detectors come online. So we've now got LIGO in Hanford and LIGO in Livingston. Virgo in Italy came online, detected its first gravitational waves in 2017, I think it was. That's a little bit shorter than the LIGO in Hanford and Livingston. Kagra in Japan, and that began its first observing run. I think it was this year, or maybe it was the start of last year. So that started to take data there as well. And Indigo, which is one planned to be in India, is not quite built yet, but it's sort of coming along. And so the more and more of these detectors we have, the more accurately we can work out where these gravitational waves sources are coming from up in space. Let's have a look at what we've detected so far. So it's not too bright there. Hopefully you can read it. I think it might be flipped on your screen. If it is, don't worry. We've got a graph behind me here. You can see there's some yellow dots, there's some purple dots as well. And these yellow dots are showing neutron stars that were discovered by more traditional techniques using the electromagnetic spectrum. These purple dots are showing black holes that have been discovered, again, using the electromagnetic spectrum. Let's fast forward a little bit. And we can see that if we go a little bit further on in time, we suddenly have found some more black holes. So those little blue ones that have appeared, you can see there's two black holes, and you can see they're being joined together into one. So that's the two black holes that are orbiting around each other, merge together, and then they merge into a larger or a heavier black hole. If we go forward a little bit further, this is operating period 2, you can see at this point we've now discovered lots of black holes, lots of these things merging together. You can also see we've discovered a few neutron star mergers as well. So if you look down the bottom here, here's a neutron star merger. We keep going further forward again. And this is the most up-to-date information at the moment. We've now discovered loads and loads of these things, right? We've discovered hundreds of these black hole mergers using just gravitational waves. Lots of these lots of neutron star mergers as well, using gravitational waves. And this is only going to get more and more discoveries as our detectors get more and more sensitive, as we sort of improve them over the years. So these detectors, they run for a little bit and then they shut down for about a year for upgrades, and they run for a little bit, they shut down for a year. This is the plan with the detectors at the moment. So if you look, we're currently in 2021, which means that most of the detectors are currently shut down. We're between operating period 3 and operating period 4. So the plan is for them all to come back online again after big upgrades before the start of next year. And so we'll start discovering even more stuff, start being able to observe even more interesting events happening up in space. Well, what about the future for this sort of stuff then? Well, ideally, what we'd like to do is make our gravitational waves detectors bigger and bigger. Now, one way to do that would be, instead of building our detectors on the Earth, why not put them up in space instead? In space, we could make the arms as long as we like. The longer those tubes are, the more accurate the more sensitive, the detectors actually are. And so up in space, we can make the arms of those detectors 1,000,000 miles longer if we like, because there's nothing in the way. And so there is a plan to do this at the moment. There's a project called LISA, and that's going to be a gravitational wave observatory, and it's going to be looking for these things from space. It's currently scheduled to launch in 2034, so we do have a little while to wait just yet. But in theory, it should work. There was a mission that went out a little while ago called LISA Pathfinder. Don't know about the details of this graph particularly, but what this graph shows us is that it should all work. The idea was that the requirements for this mission is that it should be more sensitive than this shaded region just here. And the result is this red line here, which means that it can detect it's much more sensitive than we need it to be. So basically this mission can go ahead and can actually work. We're also planning to build some big gravitational wave detectors on Earth as well. There's one called the Einstein Telescope, and this is going to be a triangular interferometer rather than an L shape like the ones we've been looking at. It's going to have 10-kilometer long arms. That's going to have a laser power of not 750 kilowatts, but of 3 megawatts. So we're talking enormous laser powers at this point. Possible for construction to begin in late 2020s with first science in the mid-2030s, so we'll see how that goes. Obviously, we've had COVID since this stuff happened, so things have been pushed back a little bit. We've got Cosmic Explorer, which again is another gravitational wave observatory, which is planned, even bigger with 40-kilometer long arms, and that would have much higher sensitivity to smaller events. So that'd be quite an interesting thing to look at. So let's finish off then with looking at the gravitational wave spectrum. So I'm pretty sure you guys are all familiar with the electromagnetic spectrum. You covered it at GCSE, and you also do quite a lot about it at A-level and AS level as well. And that's what we looked at right at the start, where we had radio waves at one end and we had gamma rays at the other end. And we change the frequency and the wavelength as we go along through that spectrum. We have the same thing with gravitational waves. And so at one end of the spectrum, at this end down here, we've got very, very short waves. So this is almost equivalent to your sort of gamma rays, right? And this is things that happen very quickly. So you might have neutron stars orbiting around each other, maybe hundreds or thousands of times a second. And they will produce gravitational waves that have a millisecond frequency or time period. Right at the other end of the spectrum, we have events that take so long that the wave period is about the age of the universe. Okay, so it takes about 14 billion years for one wave to happen. And again, just like the electromagnetic spectrum, you need different instruments to look at different parts of the spectrum. So for example, the ones we've been looking at, the interferometers, move my head out of the way here, LIGO, Virgo, those sort of things, they can detect events that happen very quickly, like these objects spinning around and merging together. LISA, that space-based telescope, will be able to detect things that take a little bit longer to actually happen. So for example, binary stars orbiting around each other in the galaxy. So not black holes, but just normal stars. At the far end, when we're looking at the really long wavelengths and the really long periods, we've got telescopes such as Planck, which is looking at the cosmic microwave background and WMAP. That might give us some information about the very, very early universe, so the Big Bang and how the universe actually came to be. So hopefully I've given you some sort of idea. I might have just blown your mind entirely, I'm not entirely sure. Some sort of idea about what's right on the cutting edge of physics at the moment. About a whole new way that astronomers have now got to look at space and to make images of the night sky. And a little bit about where we're going with this sort of stuff. I can't tell you what we're going to discover because that's the most exciting bit we don't know. Generally, if you look back in history, every time we've invented a new kind of device, we've made all sorts of fascinating discoveries. So I can't wait to find out what this new gravitational wave era opens up. All right, thank you very much. Cheers.
Thank you, Scott. That's really interesting. Just, I suppose, a couple of questions. One about your presentation more, which you may or may not know the answer to, or I might have missed it in the presentation, but you talked about LISA going up in space and said, theoretically, we can make the arms as long as we want to. Have they decided how long those arms are going to be yet?
I don't know off the top of my head. I think it's about 1 million miles is what they're looking at, which to us sounds an extraordinarily long way, right? But in space, it's not a lot. That's perfectly achievable thing to do. If you think about the sun's 96 million miles away, so it's considerably further, right? There is still an issue, of course. It's quite an exciting engineering challenge to build these things, because you can't attach the mirror to the spacecraft, because spacecrafts have all sorts of systems on them. They hum and they buzz and they vibrate and they've got coolant and all sorts of stuff going on. So what they do, which is really clever, is instead of attaching the mirror to the spacecraft, they just float the mirror in space and then fly the spacecraft around the mirror, right? Because then it doesn't have to be attached. So there's quite a clever way of doing it. That was one of the things they were testing with that LISA Pathfinder mission, just to see if that was actually feasible. But it turned out that yes, it should work. But yeah, good question.
Right, brilliant. And I suppose that one of the other questions, I suppose we move on to studying physics. Obviously, there's been quite a lot recently about people maybe going on to study something and regretting their choice later on in their lives. And I just wondered, if you could have your time all over again, would you still study physics?
Definitely.
And if so, why would you recommend it to people?
It's one of those things that I think it's one of the most sort of fundamental things we can do. So I've always been fascinated about how things work, and I was one of those annoying kids that took everything apart and they couldn't put it back together again. You know, I always want to find out what's behind the curtain, so to speak. And physics is one of those subjects that specializes in that. Well, that's what it's about. Physics is literally just the study of nature and about how our universe works. And I can't think of anything more interesting than that, to be honest with you. I know it's not everybody's cup of tea, and I'm not going to say it's easy, because it absolutely isn't. It's not something you generally regret studying after studying it. It's something you might regret studying halfway through studying it. Might be the possibility. But eventually, if it's something that you gel with, you will find it's just absolutely fascinating. And it's one of those things that you just can't get enough of. I'm sort of glued to science articles and things. Oh, what have they found now? There's like something brand new and fun that's happening kind of every week. And yeah, so I very much recommend, if you're interested in how things work, if you care about where we are in space, or why does the universe work in the way it does, or what are we made of, or anything along those lines, then it is a fascinating thing to study.
Okay. And what do you think makes a good physics student? What kind of qualities do you think you need personally?
That's a good question. So very much attention to detail. That's one of the absolute musts for this sort of stuff. A lot of things in physics and mathematics as well, it doesn't take much to get it wrong, right? And it takes little slip-ups. So attention to detail is really, really important. Some kind of aptitude for mathematics. So I'm not saying you have to be an incredible mathematician. You don't have to be Ramanujan or anybody like that, but you do have to have an aptitude for maths and hopefully enjoy it a little bit as well. Now, I must admit, I actually didn't enjoy maths that much when I first studied physics, especially when I was doing my A-levels. I wasn't a big fan. I really saw maths at that point more of a means to an end. So we use maths to do physics, if you see what I mean. So I sort of saw it in that way. Actually, later on, I started hanging out with a load of other massive nerds who studied mathematics, for example. And they really opened my eyes. They showed me some really exciting, really cool parts of mathematics. And it was only later on that I realized how interesting maths actually is as well. But you don't need to go down that route, as long as you're happy enough doing maths. I think more it's that sense of inquiry and that sense of wanting to know how things work. That's the most important thing, I think.
Yeah, okay, thank you for that. And I think I've asked this question at the end of every Uni4Me session. A lot of students might be a little bit worried at the moment, thinking about going to university, in respect that because of the pandemic, they might not have completed the whole course. Is that something they should worry about, or is that something that universities will help them with once they're there?
Yeah, I mean, so just want to start by saying that everybody I've met, all the students I've met for sort of A-level students and GCSE students, you guys did an absolutely incredible job in very, very difficult circumstances. I don't envy you guys at all. So well done for getting through this. That's the first thing to say. It does feel, okay, I'm not going to go too far, but it does feel like we're coming out the other side of this now. And let's hope by next year that you will get sort of university experience that everybody wants to have. With regards to sort of things that you might have missed, universities are well aware of the situation. The universities have been closed as well, and we've been struggling to make sure that our students get the best possible result, the best possible education as we go through things. They will do everything they can, or at least I can only speak for Imperial, but I know at least for Imperial, we'll do absolutely everything we can to make sure that you're not overwhelmed, that you are given the information, the resources and the time that you need to catch back up again. This isn't done normally anyway in certain aspects. So even if you come to and you do a physics degree at a general university, we can generally assume some kind of level of physics, but even then you get a very wide range of abilities and a wide range of achievement and all sorts coming into the university. So they do tend to start with as low as they can and build up. Okay, so don't panic. You're in the same boat as everybody else, right? Very few people have had a normal year of any description for the last couple of years. So we understand and we're working hard to make sure it works for you guys.
That's great. I'd just like to thank you again, Scott, for your time this afternoon. It's been absolutely fascinating. So thank you very much indeed.
No problem. Thanks for having me, Martin. Appreciate it.